Hello guys, welcome to this new video. So now we are going to work through the paper 1 in the 2025 Specimen paper. So to begin with, question 1 says we have a car traveling at an initial speed of 16 meters per second and it is decelerating at 4 meters per second squared. We need to calculate the distance traveled. Well, here we can use the Suvat equations, specifically this one. We know the final speed, as when we stop, it will have a speed of 0. We know the initial speed, we know the acceleration, so we can easily calculate the displacement. So 0 squared is equal to 16 squared plus 2 times minus 4, as we are decelerating, times the displacement. And so we'll have 16 squared being equal to 8s. And well, you can just use your calculator to solve this, or you could use the fact that 16 is 2 times 8, so you can say 2 times 8 squared is equal to 8s, and so 4 times 8 squared is equal to 8s. One of these 8s will cancel out, and so we get that s is equal to 32 meters. Or you could just plug it into your calculator. Then we have a block of mass 2 kilograms accelerating without changing direction. We need to calculate the impulse acting on the block. Well, impulse is the change in momentum, and so it's going to be the force times the change in time. So we need to calculate the, well, this is one way to calculate it, but another way we could calculate it is just simply mass times delta v, as at the end of the day, momentum is m times v, and the mass isn't changing, the velocity is changing from 15 to 20, so delta p will just be the mass of 2 times final speed minus initial speed, which will give us 10. And then now we have a net force of 8 newtons on a body of 4 kilograms. It accelerates it from a speed of 0 to a speed of 5 meters per second. What is the work done by the force? So, well, what we can do is first of all calculate the acceleration that it's experiencing. We know that there's only one force acting, so the net force is 8. And from Newton's second law, we know this is m times a. We know the mass is 4 kilograms, so our acceleration will be 2 meters per second squared. So again, we can use the same equation from the first question. So v squared is equal to u squared plus 2as. We know our final speed is going to be 5 squared. Our initial speed is 0, and then 2 times the acceleration times the distance traveled. So from this we'll see that the distance is 25 over 4. And well, work is just force times distance. So we know the force being applied is 8 newtons, distance is 25 over 4 meters, so this will just be 2 times 25, so 50 joules, which is A. And then we have a disk of mass m, radius r, on a frictionless table, and we have two forces acting on it, and we're given the moment of inertia. We need to calculate the angular acceleration of the disk. Well, if we remember, the torque is equal to the moment of inertia times the acceleration. And well, we know that we can calculate the moment of inertia as we have the formula for it, and we can also calculate the torque. So the angular acceleration will just be the torque divided by the moment of inertia. And well, how can we calculate the torque? Well, here we have two forces acting, and they both act at a distance of r from the rotational axis. So the torque by, for example, this force will just be the force times this r, because this is the perpendicular distance to the axis, and we see that both forces try and rotate in the same direction. So this means that we can just add the two torques up. So the torque will be F times R times 2, so 2Fr, as they both try and rotate the disk in the clockwise direction in this case. And then we divide by the moment of inertia, and then we find that this the one of the r's will cancel out, the 1/2 comes to the top, so it'll be 4f divided by mr, which is d. And then here we have a very typical elevator question. This has come up multiple times already in paper ones. So we have the total mass of the elevator, we know the acceleration, we need to calculate the tension. So usually here we want to start with drawing the free body diagram. So you have the tension, we have the weight. So the net force will be the sum of these two forces. And well, the tension is pointing upwards, and we have a acceleration upwards, which means that the tension must be larger than the weight. So if we want a positive net force, we should do tension minus the weight. And we want to calculate the tension, so that will just be F net plus W. Well, F net from Newton's second law, we know is just the m times the acceleration of the whole system. Then we add the weight, mass is 800, acceleration is 2. Then we add the weight, which is 8,000. So that's 8,000 plus 1,600, which is D. Alright, now we have an object at rest at a height h above the surface, something like this. And as it falls, it passes a height of 0.75 h. So we have lost a quarter of our height. It has fallen 0.25 h. And we need to calculate the ratio of the kinetic energy of the object at this height and the potential energy at height h. Well, we know that energy is being conserved, so if we just consider these two cases here, if we name this 1 and this 2, then let's say we introduce a new height over here. Let's say this is height equals 0. Then here at situation 1, we only have potential energy, and at situation 2, we have kinetic energy. But since energy is being conserved, these two must be equal. So the amount of potential energy we lost is equivalent to 0.25 mg. So we can say that the kinetic energy at 0.75 h is just the height times g times mgh. As this will be equal to the kinetic energy there, as everything is conserved. And then we need to divide this by the potential energy at the top, which will just be mgh. And well, this is not 0.25 technically, this is 0.25 times h, as that's how much we've lost a fourth of it. So we see all of this cancels, and this will just be 1/4. So B. And then here we have a cylinder of mass m, radius r, rotating at some angular speed omega. And we know that the rotational kinetic energy is K. And we also given the moment of inertia formula. And then we have a new cylinder of double the mass, double the radius, and double the angular speed. What is the rotational kinetic energy? Well, E rotational is just 1/2 I times omega squared. We see this from our data booklet. And well, we know that the moment of inertia is 1/2 mr squared. So 1/2 mr squared omega squared. And well, we double the mass, we double the radius, and double the angular speed, but the radius and the angular speed is squared. So this is 2 times 4 times 4, which is 16 times 2, 32. And then here we have a bird of weight W. We need to see the relationship of the tension with this weight. And well, we can see that there's like a little bit of like, they're not horizontal. So if we imagine the tension along this rope over here, tension is always along the rope, as long as we have simple forces acting. So what we can see here is that since we're at equilibrium, the sum of the forces must be 0. So if we were to split this tension force into a Tx and a Ty component, then we will also have this on the other side. So if we technically have tension in both ropes, and due to the symmetry, it's the same in both ropes. So we can see that the ty's, the two ty components, will have to cancel out with the w. So those two already have the magnitude of w, but we also have a tx that is being cancelled out in both ropes. So if we know that ty is the same magnitude as w, and we have some non-zero component here, then the hypotenuse of this triangle is the tension, and that tension will always be larger than ty. As in a right angle triangle, we always have the hypotenuse the longest side. That's always how it works. Can't really be any other way. So the tension must be greater than w, as ty is, well, the two ty components will just form w. And then here we have a spacecraft moving with speed v relative to Earth. This is Earth. We have a spacecraft moving with a speed of v, and it reaches some planet. And in this situation, both clocks read 0. And the distance, according to people on the Earth, is d. And what are the readings on the clock on the Earth and on the spacecraft? Well, on the Earth it's simple. We just have something moving with a speed v for a distance of big D. So the time will just be distance over velocity. And well, for the spacecraft, the distance is going to change a little bit. Well, not the distance, but the time. And if we look in our data booklet, we see that there's this relationship that delta t is equal to the gamma factor times the proper time. And well, if we consider the spacecraft system at the moment, then this proper time will be from the perspective of the spacecraft, as proper time is just the time measured by the observer that's like that we're investigating technically, so people on the spacecraft. So this is for the spacecraft. And this is the delta t we want to find. So we see that delta t is equal to the normal delta t divided by gamma, where this delta t is just the measurement made by some other observer, in this case the people on the Earth. And we know that gamma is equal to 1 over the square root of 1 minus v squared over c squared. So if we just do this, we see that, well, delta t will just d over v, and then 1 over the gamma factor will just be 1 over this, so the root of 1 minus v squared over c squared. So A. I didn't mean to circle it already, but yes, A is correct. I meant to circle this and then this, but yes. And then the internal energy of a gas, well, that's just the sum of the intramolecular and the total kinetic energy of the particles. So the potential and the kinetic energy is something you have to memorize. Comes up both in paper 2 and paper 1, so worth remembering. And then we are told that a gas undergoes one cycle of a cyclic process. So let me just draw some example of a cyclic process. Let's say this. This is the starting point, and let's say it goes this way. And the net change in internal energy of the gas, well, is going to be 0. As in a cyclic process, the starting point and the ending point is the same point. So the gas is in the exact same state before and after. So the internal energy cannot differ in any way. We can also consider this formula that the change in internal energy is 3 over 2 nkb times delta t. But since we're again at the same point, the delta t is just 0, so temperature cannot change. And then we have a working refrigerator with the door open in a sealed room. The entropy of the room increases. Probably the easiest way to see this is that we introduce new particles. So the randomness of the room will increase as we have new particles flying around the room, so more random, more chaotic. And then here we have black body radiation of 600 Kelvin. And what is the radiation curve for 450 Kelvin? Well, what we need to notice is that smaller t results in smaller intensity. So the peak intensity must be smaller, so this is incorrect and this is also incorrect, as the dotted line shows the original graph, and here the peak intensity is larger. And then we also know from Wien's law that lambda is proportional to 1 over t. So this is like the maximum wavelength, or the wavelength of the highest intensity, so to say. And then we see that we decrease the temperature, so the peak wavelength should increase. So this was the peak wavelength before, but now this peak wavelength has increased as we have decreased the temperature. So it's A. And then here we have a star X, luminosity L, apparent brightness B, and this is a distance X from Earth. And star Y is same brightness, but 4 times more luminous. Well, we know that luminosity is just the apparent brightness divided by 4 pi times the distance squared. We also know that Lx is equal to 4 times Ly, and we know Bx is equal to By. They have the same apparent brightness. And well, so we can rearrange for B. So we know that B is equal to L 4 pi d squared. And we know that Bx and By are equal. So, well, 4 pi will just cancel out. So we'll have Lx times dx squared is equal to Ly times dy squared. And we know Lx is 4 times Ly. So 4 times Ly, dx squared is equal to Ly dy squared. Ly's very nicely cancel. And then we can take the square root of both sides. So we get rid of the squares. So 2 times dx is equal to 2 dy. So we see that dy is double the distance of dx. So 2d. As this dx is just the distance from x to the Earth. Now here we have a nice resistor question. Each of resistance R. And we need to calculate the effective resistance between P and Q. So we can imagine like 2 wires coming from here. And this is the circuit. So what we see, we need to first decide what is in series and what is in parallel. And if we imagine these 2 wires over here and some current flowing in this wire, then how we can decide is that if the same current flows through every resistor, they're in series, but if the current has to sort of split before it goes through the resistors, then well, they're in parallel. And well, we see that here there's a junction. So if this is I, then it will turn into I1 and I2. So we see that the current going through these 3 resistors will be different than the current going through this resistor, as there's a junction over there. Another way we could redraw this, perhaps it will be easier to notice or easier to see the relationship. This is the exact same setup as that is drawn in this question. So I'm assuming like this, it's much more obvious to see what is going on. But again, here we have current coming in, and then I1 going up, and I2 going down. And then I1 goes through these, and I2 goes through these. So these are series, but they're 2 in R in parallel. So this has 3R, and then we have a 3R and a 1R in a parallel. So 1 over R E equivalent is equal to 1 over R plus 1 over 3R. So that's 3R plus R over 3R squared is equal to 1 over RE. So RE is equal to, well, we can still say 1 over RE is 4 over 3R, as the R's cancel out. And then RE will be 1 over this, so 3R over 4, which is A. And here we have another circuit question. We have a conductor X connected to a cell of EMF E, and a power of 16 watts is dissipated here. And then conductor Y is the same material, same diameter, but twice as long, and the EMF is twice. We need to calculate the power dissipated in Y. So we know that R is equal to the resistivity times L over A. And while the area is the same, the length is doubled, so the resistance has doubled. As if the length doubles, the resistance doubles. But we know that V is equal to I times R. This has doubled, the voltage has doubled, the resistance has also doubled, so the current remained the same in both circuits. So we can use the formula I is equal to I squared times R. This is the power. This is just the same in both circuits. and well, we have double the resistance in the second circuit, so we'll have double the power, so 16 times 2, C. Now here we have two containers X and Y, filled with an ideal gas at the same pressure. The volume of X is 4 times the volume of Y, Vy, and the temperature of X is 327, temperature of Y is 27, amount of substance in X and Y. So we know PV is equal to nRT, so N is equal to PV over RT. Pressure and the gas constant we don't really care about, they're just constant everywhere, so they would cancel anyways. So N is equal to V over T. Whenever we only talk about ratios, we can usually always cancel out whatever's constant, as they would just be on the top and on the bottom, so they're gone anyways. So we need to do Vx over Tx divided by Vy over Ty. This will be Nx over Ny. So we know that Vx is 4 times Vy, so we can say 4 Vy over here. And well, here we first need to convert these temperatures into Kelvin, as we always work in Kelvin. So we add 273, will be 600, this will be 300. So we can see that Tx is equal to 2 times Ty. So this will be 2 Ty divided by Vy over Ty. All of the letters cancel, so we just end up with 4 over 2, 2. And then here we are told electromagnetic wave is a wavelength about the size of the diameter of an atom. So this you just have to know is approximately 10 to the minus 10. And then you can look in your data booklet and see that X-ray has a wavelength corresponding to this. And then here we are told that a particle undergoes simple harmonic motion of period t. Time t equals 0, the particle is at its equilibrium position. What is the t when the particle is at its greatest distance from the equilibrium position? So we know that simple harmonic motion is a sine or a cosine graph, but we are told that at t equals 0 it's at equilibrium. So let's say that we have a sine graph, and this is t, so this is one period. Then this means that this is t over 2, this is a fourth of the period, and this is 3t over 4. So greatest distance from the equilibrium position is here and here, so either t over 4 or 3t over 4. We only have 3t over 4, so C. And then here we have a diagram showing variation of position of the displacement of a standing wave formed on a string. Diagram shows the position displacement of a traveling wave moving to the right. Yes, and all these points are on the string, obviously. What is the phase difference between P and Q, and the phase difference between R and S? So between P and Q in a standing wave, we must know that particles move up and down of constant amplitude. So they just move up, down, up, down, up, down. And here, this whole part of the wave is going to be moving up at the same time. So P and Q are in phase. They have no phase difference. And in R and S, this is going to be a little bit more tricky to see. But if we see that the wave is traveling to the right, that means if we draw the next instant of time, it's going to look something like this, as the wave has shifted over to the right. And we know here as well, particles only move on vertical lines. These particles only move up and down. It's in transverse waves where the particles move to the left and to the right. Here, they only move up and down. And well, we see that for R to remain on the wave, it must move up, as the new position of the wave will be above R, whereas S will have to move down. So this shows that they are actually out of phase, and well, one of them is moving up, the other one's moving down, so they're at a phase difference of pi over 2. So that is C. Question 21. We have a mass of 250 grams hanging from a spring constant of 4 Newton per meter. We need to calculate the natural frequency. Well, the natural frequency is just the frequency that it would want to oscillate at. So that would be technically the frequency at which its amplitude would be the largest. But usually that's the case we always have to consider, except when we talk about damping, but we don't have any specific formulas for damping. So we can calculate the period of a spring mass system with 2 pi m over k, and we know that frequency is 1 over the period. So this will be 2 pi times root of 1/4 over 4. So that's going to be 1 over 16, and then the square root of that is 1 over 4. So this will just be pi over 2. And then 1 over the period will be 2 over pi then, which if we plug into our calculator will give something around 0.64. And next question, we have light from a source incident on a single slit, resulting in this diffraction pattern. And then the intensity of the source is the same, width is increased. We need to see which graph correctly shows the variation of intensity. Well, firstly, we need to remember that the angle of the central maximum, so the angular separation of the central maximum, is lambda over b, where b is the width of the slit. So if we decrease the width of the slit, then this fraction itself will become larger, so the angle will increase. And so, oh no, sorry, it's increased. That's why it didn't make sense to me. So the width is increased, not being decreased. So if we increase the denominator of the fraction itself will become larger. So the angle will decrease. So it will become more narrow, technically. So only A or C could be correct, as in the other two is becoming more wide. And then, well, if we increase the width of the slit, we're going to have more light incident on the screen, as if we have a larger gap, then more light can come through, so our intensity will also increase. And so the answer is D. And then here we have another monochromatic light incident now with a diffraction grating. We form a diffraction pattern, and only the first order maxima can be observed. And what do we need to change so that we can also observe the second order? Well, we know the formula we like to use for diffraction gratings is b sine theta is equal to m lambda, where b is 1 over the lines per millimeter, so how many lines we have in 1 millimeter, m is the order, and lambda is the wavelength. So we want to find m, we want to find the relationship for m, so m will just be b sine theta over lambda. And as I said, b is just the lines per, well, b is 1 over the lines per millimeter, so we usually use n for lines per millimeter. So it will be sine theta over n lambda. And we want to increase m, so we want to somehow increase this fraction. So first option says decrease the distance between the diffraction grating and the source of light. Well, that variable isn't in this equation, so cannot be. We can also increase the distance between the diffraction grating and the screen. Similar reasoning. It's not even in the formula. And then in C it says increase the wavelength of the monochromatic light. Well, if we increase the wavelength, the fraction becomes smaller, and so the order will also decrease. So there's no way we can observe a larger maximum, so the answer will be D. If we reduce the number of lines per unit length, so this is what is known as N, then if we reduce this, the fraction becomes larger and the orders also increase. In question 24, we have a solid metallic sphere, positively charged, and the electric potential due to the sphere is constant inside the sphere. So again, this is something that we just have to remember. We can also see this from a graph that goes something like this, where this is like the radius of the sphere. So inside is constant, like this. This is like the distance from the sphere. So it's obviously not constant outside of the sphere, as it varies with a 1 over x type of relationship. It's smallest at the surface of the sphere. Again, that's not necessarily true, as it's constant, and this is where is the highest, so it's technically the largest on the surface, and increases with the distance of the sphere. Well, we can see that the potential is decreasing, so that is also incorrect. Then here we are told a planet orbiting a sun in an elliptical orbit. At the position shown, which quantity is decreasing for the planet? Well, the acceleration can be calculated by v squared over r. This comes from the fact that if we know, then I think this is easier to remember that the centripetal force is mv squared over r, and then we know F is equal to ma, so m times a, so this is a. And well, here the speed is also increasing, but the distance is also decreasing, so they kind of cancel each other out over here. So I mean, yeah, so the speed increases and the distance decreases, so the acceleration will be increasing. As this increases, this decreases, so overall it must increase. And the angular momentum is mvr. Again, speed is increasing, radius is decreasing, so it either remains constant or the speed is increasing and at a larger rate. Kinetic energy is 1/2 mv squared. Again, speed is increasing, so cannot be, because we want it to decrease. And then gravitational potential energy. Well, we know gravitational potential energy is minus gmm over r. And our radius is, our distance is decreasing, which means that the fraction is increasing, but since we have a negative sign, we're getting a larger and larger negative number. So that means that we are decreasing the gravitational potential energy. So fraction increases. So the fraction, like the absolute value of this increases, but we have a negative sign. So like maybe before we had like -5 potential energy, so the absolute value here is 5. So the magnitude of the potential energy increases, but since we still have the negative sign, the potential energy decreased. So like this. Then question 26, we have two parallel wires. They have a force of F in the first case, and then we double the distance and we half one of the currents. And we need to see what the new force per unit length is. Well, force per unit length is just this constant times I1 times I2 over 2 pi the distance. So if we see the new currents on the top, the first current is the same, the second current is halved, and the distance is doubled. So what we see is that this will overall be 1/4. So the force will be a fourth. But this can also just be seen from the fact that since we decrease the current, the force must decrease, and we increase the distance, so again the force must decrease, and then we can just see whether it's 4 or 8 or 2. So yeah, which we can do with this formula. And then here we have a point P in a uniform electric field. What is the direction in which the electric potential increases at P? Well, it's B. We need to remember that electric field lines always point from high potential to low potential, always. So if we remember this, we see that an arrow pointing up will point towards the direction that the potential increases. And then planet X and Y orbit the same star. Average distance between planet X is 5 times greater than the average distance between planet Y. We need to come up with the orbital period of planet X over Y. Well, we can, this is again very often used. So if this is, let's say, the star and this is planet X and it's orbiting, then the only force acting on it is the gravitational force. And since it's moving in circular motion, there's also a centripetal force. So we can say that the centripetal force is equal to the gravitational force. We see that the m cancels out. This r cancels out with this. So we see that v squared is equal to gm over r. And we also know that v is the distance over time. So the velocity of oscillation is the distance covered divided by the time taken. And for circular orbit, the distance is just the circumference of the orbit. So the circumference of a circle, which is 2 pi r, where r is the radius of the orbit divided by the period. This is all squared, and then gmm over r. And then we kind of want to solve for the period. So we can take the square root of both sides, and then, well, maybe it's easier if we do this in multiple steps. So we can just do 2 pi over t, and we take the square root. So we'll have gm over r divided by r. And well, we can bring this r inside the square root, as if this would be r squared under the root, then we can just divide the two fractions. So we'll have r cubed over here. And then the period will just be 2 pi times 1 over this radical, so r cubed over gm. So this is the period in terms of the radius. And we know that the radius for x is 5 times larger. So we see that it varies with the square root of r cubed. So it will just be root of 5 cubed as we increase the radius by 5. And so the orbital period of planet X will be larger by this factor. So d. And here we have a rectangular conducting coil rotating at constant angular velocity. And at one instant, the plane of the coil is at an angle of theta. The magnitude of the induced EMF in the coil is never zero. Well, that's not true, because if we think about some graph, this is going to vary either sinusoidally, like a sine graph or a cosine graph, whatever we took as the initial condition. And well, it is zero in multiple places, so that's not true. And then we need to see when it's maximum. So we're given 3 options here. We know that the induced EMF is equal to the rate of change of flux. And well, the rate of change of flux is largest when we go from 0 to a value, as that's when the largest change happens. And we go from 0 to a value when our coil is parallel with our our magnetic field. Because if it continues rotating like this, or yeah, if it's rotating, then it rotates into some position like this and then continues rotating around, then in that instant the magnetic flux will go from 0 to some value that is not 0, and that is when the maximum change happens. So when it's like this, the angle is 0 as they're in the same plane, and yeah, and 180 is the same situation, just flipped. So this is when, but like if it's like 90 degrees, which is like almost what is shown over here, then we have, just because we have the maximum flux going through it, doesn't mean that we will have the maximum induced EMF, because the maximum induced EMF isn't equal to the amount of flux, so the amount of field lines going through the loop. It's about how the number of field lines changes over unit time. And that's maximum when we go from 0 field lines to some field lines. Then we have a spherical planet of radius r0, and this graph shows the gravitational potential due to the planet from a distance r from the center of the planet. So this is the surface of the planet, as this is at r0. We need to calculate the escape speed from the planet. Well, if we look in our data booklet, v escape is the square root of 2 gm over r. And we might notice that this is actually potential, gm over r. So we can say that the v escape is equal to root 2v, where v is the potential of the planet at the surface. And well, very nicely we can read this off, because we know the potential of the surface is 5 times 10 to the 6 joules per kilogram. So this will just be the square root of 2 times 5 times 10 to the 6. This will be 10 root 10 times 10 to the 3. And if we plug this in, we should get 3.2 for root 10, which is C. And here we have a charged rod brought to an initially neutral metal sphere without touching it. And then we ground it, so we allow charge to flow to Earth. And the ground connection is removed, and we need to deduce the charge on the rod and the induced charge on the sphere when the connection is removed. So we see direction of conventional current. Conventional current is the direction in which positive charge moves. So this again is just something you need to know. In circuits as well, we use conventional current, because that's just the direction the positive charges will move. Because in earlier times when they were investigating this electricity stuff, they decided to take the direction of the current in which positive charges move. Nowadays we don't know. Nowadays we know that positive charge don't really move. It's the electrons. So the electrons are technically moving the other way, but it's besides the point here. We just always take conventional current. So if positive charge is flowing here, it means that something is repelling the positive charges from here into the Earth. So that means that the charge on the rod must be positive, because in that way the positive charges will repel and it will push all of the positive charges from the sphere into the Earth. And so the remaining charges will be negative. So C. So the charge induced will be negative. In question 32, we have a positive point charge of magnitude 1 microcoulomb and a charge q are separated by distance d. An electron is placed at a distance d from the 1 microcoulomb charge. The electric force on the electron is 0. What is q? Well, F electric is k q1 q2 over r squared. So if the net electric force on the electron is 0, then let's label this charge 1, charge 2. Then since this is positive charge and this is a negative charge, they will attract each other, so the force will be this way. So this, let's say this is F1. And if we want a net electric force of 0, we need some other force of the same magnitude but other way. So this will be F2. And well, so this charge has to be negative because that's how they will repel each other. So it's either A or B. And well, we want the magnitude to be same as F1, but the distance is double that of F1. So if we would have the same 1 microcoulomb charge, then because the distance is double, the force would only be a fourth. So it would be F over 4 because it varies with the distance squared. We see from this formula. So it would be 2 squared, so 4. But we want the same force, so we need 4 times the charge as well. So the 4 times the charge over here. And so A has to be minus 4. So that 4 over 2 squared will result in the same force. And then we are asked for the sequence of evolution of a main sequence star of about 2 solar masses. Well, this is just something you got to remember, these evolution processes, these sequences. And then in question 34, we're given an emission spectrum, and we're asked which of the following is the atomic energy levels that produce this spectrum. Well, what we need to know about these spectrums is that these show the energy levels of our atom, and electrons can be transferred from in between these energy levels, not in between them. So we cannot have an electron on this level dropping here, because what's here? Nothing. It cannot just drop to nothing, so it has to drop to some other level. It always has to drop between levels. And so we can calculate this energy, so like the change in energy, or like the photon emitted, is when an electron drops like this, it emits a photon. And that's how we can measure this wavelength of the emitted photon. So this change in energy will just be h times f. So the difference in the energy levels will be equal to the h times f, so the energy of the photon, which is just hc over lambda. If we use that c is equal to lambda f. So we can rearrange for lambda, so we'll just get hc over delta E. So we see the larger the energy difference in the atomic energy levels, the smaller the wavelength emitted will be. So we see that we have two lines over here that have a very high wavelength. A very high wavelength must mean a very small energy transfer, and they're very close, so the energy transfer is approximately the same. And so that means we need two levels in a diagram like this that are about equally separated, equal distance. So if we look at these two, well, the delta E for these two processes is approximately the same, and both delta E's are very small, so we'll have a very high wavelength. And so that's why there are two lines over here. If we look at this one, for example, we don't have, these are all the same, so it's not like we have two delta E's that are much smaller than the other ones. Here we only have one delta E that's very small. And then we could look at similar ones, so like the largest energy would, for example, be this one, or for example, these two lines would be like going from here to here and from here to here. So again, we have two lines that are very close to each other. So that's how you can deduce that it should be A. And then question 35, we have a photon of wavelength lambda scatters off an electron. So we have some photon, electron, wavelength lambda, and it scatters off with a wavelength of lambda prime. What is the incident photon energy that gets transferred to the electron? Well, the energy transferred will just be the incident energy, so the energy of lambda, minus the energy of the lambda prime. So this is how much has been transferred, and we want to find the fraction of this compared to the incident energy, so divided by E lambda. And well, from the previous question, we can also see that energy is just hc over lambda. And this will be hc over lambda prime divided by hc lambda. And then very pleasantly, every hc cancels out, gets out of the way. So we'll just have 1 over lambda minus 1 over lambda prime divided by 1 over lambda. So on the top, we bring two common denominators. So lambda prime minus lambda over lambda prime divided by 1 over lambda. So we see that this cancels with this. So we're just left with lambda prime minus lambda over lambda prime. So D. In question 36, we have some statements about nuclear fission reactors. First statement, the heat exchanger transfers energy from fuel rods to the moderator. Well, this is immediately incorrect. This heat exchanger only transmits energy from the reactor to the steam engine that heats up the gas. So if we know 1 is incorrect, we can already say C, but we can also see that 2 is control rods must be good absorbers of neutrons. The task of the control rods is to change the speed of the reaction. So if the reaction gets out of hand, they drop in some control rods, they eat all of the neutrons, so less neutrons will be causing fission reactions, and so the reaction will be slowed down. And the moderator is to slow neutrons down, and that's also true because if the neutrons would be too quick, they wouldn't be inside the reaction chamber for long enough, and there would be a very low probability of them hitting, for example, a uranium nucleus. So if they slow down, then they will be inside the reaction chamber for longer, so higher chance of collision causing fission. In question 37, we're given a HR diagram of x and y. What is the radius of x over radius divided by radius of y? So we see that they're on a horizontal line, so L is same for both. And we know that the luminosity is just sigma a t to the fourth, where a is the surface area of the planet. So this is sigma 4 pi r squared t to the fourth. And we know that L is the same for both. So we can rearrange for r, and r squared will be just L over t to the fourth. Again, we can just honestly neglect all of these constants as we're again finding a ratio and they will just cancel out anyway, so it's not worth bothering with it. So we see that r will be just the square root of L divided by t squared. And we want rx over ry. So this will be the square root of Lx divided by Tx squared divided by square root of Ly divided by Ty squared. We know Lx and Ly are the same, so these are also gone. So we end up with Ty squared divided by Tx squared. And well, we see that Ty is a fourth of Tx, so this will be 1 over 4 over 1 squared. That's 1 over 16. So that is A. And then 38, we're given that the energy level of nth level of hydrogen is given by minus E0 n squared. What is the frequency of the photon emitted in the transmission from n equals 4 to n equals 2? Well, again, we know that the energy is just h times f, and this is the final energy minus the initial energy. And so we know that the final energy is at n equals 2, so, or well, yeah, so what is the frequency of the photon emitted in transition from n equals 4 to n equals 2? So technically, we can say that the final is the n equals 4 level because this will be negative. So, or we can just do it like this. So E final is so E0 divided by 16 plus E0 over 4. So this is our final level, and because of the double negative, this becomes a positive. So it should be like this. So the final energy is this at n equals 4. We can look at it the other way. So n equals 4 is the final and n equals 2 is the starting. That will just be the change in energy, and this way we'll have the correct sign. as well. We could have done it the other way as well. We just end up with the negative version of this. So we just add these two, we bring to common denominator, so this will be like, what, 16 over 4, and so this will be 3 over 16 E0. And so, yes, so HF is equal to 3 over 16 E0, so F is equal to 3 over 16 E over H. So that's B. We could have also done that the final level is n equals 2 and the starting is n equals 4, but then we would have just had this expression with a negative sign in front. So we could have just realized that it should be the other way. And then now we have another monochromatic light of frequency f1 incident on a surface of metal. Stopping voltage is V1. When the frequency of the radiation is changed to f2, the stopping voltage is V2, and we need to find this ratio. So we know that the work function of a metal is just the energy required to bring an electron from inside the metal to the surface of the metal. And that is just equal to the incident photon energy minus the maximum energy of the electrons emitted. This difference will tell us how much energy we need to expend just to remove an electron from the surface. And since we're using the same metal, we know that the stopping potential of both equations or both situations is the same, as stopping potential is constant for a metal. It's not relevant to what we're shining on it. So we can say that HF1 minus and E max is just the stopping potential times an electron volt. So this can be measured in electron volts. That will be the units of energy. So electron volts are also units of energy. This is how we can calculate it. So HF1 minus EV1 is equal to HF2 minus EV2. So we can bring the similar stuff to the same side, like this, and then EV1 minus EV2. So we can factor out the H and the E. So H times F1 minus F2 is equal to E times V1 minus V2, like this. And then we want V2 over V1 minus, so we have to divide by E and divide by this. So H over E will be equal to V1 minus V2 divided by F1 minus F2. And I think it should be, well, yeah, so it's the same because I just got it the other way. So if we multiply both the top and bottom by a negative sign, then we will find what is required. So minus minus, then technically we didn't really do anything because we did the same to the top and bottom, but then we'll have V2 minus V1 over F2 minus F1, which is technically what we had to show. Yes, and then the final question in this paper, we're given an alpha particle of some initial energy, and it moves towards the center of a nucleus, of a gold nucleus. What is the distance of closest approach? So if we imagine what's happening here, this is gold. We have an alpha particle, and it got shot from like infinitely far away with some kinetic energy, and it got to this distance, and here the speed is 0, so we only have potential energy. So the kinetic energy of the alpha particle got transferred into potential energy, and so because here we have 0 speed at the end of closest approach, that's when it comes to a stop. So we only have potential energy, and so we know potential energy is just K Q1 Q2 divided by R. This is equal to the kinetic energy, which was 5.5 mega electron volts. So all we need to do is plug in now and convert some of the things. So K is 9 times 10 to the 9. Q1, well, the charge of an alpha particle is 1.6 times 10 to the minus 19. But since we have 2 protons, we need to multiply this by 2. And then similarly with the gold nucleus, 1.6 times 10 to the minus 19 times 79, as we have 79 charged particles, so 79 protons. This is all divided by the distance, and this is equal to the energy. Well, it would be nice to have this in joules as we're working with SI units. So we first convert it into electron volts and then into joules. And then if you plug this into your calculator, you end up with 4.1 times 10 to the minus 14 meters. So this was the end of this paper. If you want, you can see all of the solutions here as well. If I got anything wrong in the workthrough, you can see what the official answer is here, and if you have any questions, feel free to leave them in the comments. And yeah, I hope I was able to help, and see you in the next video.